Scott Smith here. We talked a lot about gravity last term. This term we're going to talk about electromagnetic forces and how charges behave in the presence of electromagnetic fields. Okay, so let's talk about this idea of charge. Charge is fundamental to understanding electromagnetism. And you already probably know a little bit about charge from maybe chemistry or physical science classes. So one electron, one proton has a charge on it. A neutron turns out to have no charge on it, and that's where it gets its name, of course, neutral. So one electron gets its charge from 1.6 times 10 to the negative 19 coulombs. A proton, oh, this is negative. A proton has exactly the opposite. 1.6 times 10 to the negative 19 coulombs, okay? And then the neutron is 0. Okay, this capital C, this thing is called a coulomb. And that's a measure of charge. And so one electron is a pretty small amount of charge, but we have a lot of electrons, we have a lot of protons floating around. So the rules for charges are the following, and it's really easy to remember because we all know likes repel, right? Likes repel, and opposites, come on, fill in the blank. Likes repel, opposites, right. And so if I take two negative charges and I put them right next to each other in space, they'll repel. There's a force trying to push them apart, okay? If I take a positive charge and a negative charge, there is a force, an attraction between them trying to pull them together, okay? But we know we have to have equal and opposite forces. So if I have F to the right on this one, I know I have to have F on the left on that one. And if I have F to the right on the negative charge, I have to have F to the right on the positive charge. Equal and opposite forces, all right? Now this configuration right here, this one, actually, I'll just do it again down here. Does anyone recognize what that is? Does anyone know what that is? Right here? Where do you find a positive and a negative charge right next to each other? Where do you see this? Where have you seen this before? You, in the orange shirt. What are we made of? Come on. Like in the universe. Where might you find a positive charge and a negative charge right next to each other? Ah, an atoms, exactly, yes. This is an atom, okay? So we're going to look about a famous physicist had once had an opportunity to twit an alien nation, okay? And of course, this guy's a genius. And but when he twits, you have to put everything into one sentence. And there's one sentence that he sent to this alien race. He probably sent it in binary code so they could read it. But I think it's pretty cool. He put atoms. If you had to say one thing and you could write it to an alien race, he said, atoms. What did he say? Let me look at his twit. This is old tech here. Stuff is made of atoms. Okay? Which means it just has a positive charge and a negative charge, and the negative charge is whirling around the positive charge. Okay? So this would be a great starting point just for thinking about the atom. Okay? One proton, so that means it's hydrogen, number one on the periodic table, and the electron is whirling around this proton. And in the ground state, it's more or less whirling around in a circle. Now, when you get to quantum physics, of course, it's more complicated. You can't really talk about it having a specific point, the electron, a position, and going around. It gets a little fuzzier because the wave functions in the cloud of the electron. But it's just a good starting point for thinking about a hydrogen atom. But when something's moving around in a circle, no matter what, there has to be a force. All right? Circular motion tells us there has to be a force keeping this going in the circle. And if it's the Earth going around the sun, it's gravity, right? Keeping it in its orbit. But here, it's, of course, a different force. It's the electromagnetic force. Likes repel and opposites attract. All right, the electron is bound to the proton because of this force that's holding it there. Okay, so let's look at the actual Coulomb's law. So Coulomb's law, it says the following. It says force is equal to K, Q1, Q2 over R squared. What are these different things? What is this? Okay, K is a constant. It's Coulomb's constant. It's 8.9 times 10 to the 9. And then it's got some funky units on it. I mean, you can sort of figure out what the units have to be. Okay? K is sitting up here, so I got to end up with newtons. I got an R squared on the bottom, so that's going to be a distance. So meters squared up at the top. And then I have Q1 and Q2, which if I said the charge was in coulombs, there must be coulombs squared on the bottom. Okay? And this is Coulomb's constant here. There's other digits here. You could add other digits. It's like 8.98. But we often just say it's 9 times 10 to the 9th. Okay? What about Q1? Q1 is the charge of the first particle. And then, of course, Q2 is the charge of the second particle. And then finally, R is the distance between them. Oh, yeah. It's the distance between these two charges, distance between Q1 and 2. And this is Coulomb's law. It's going to apply to a great number of cases that we're going to talk about, a lot of those in this term. And then later on, we'll see where this all starts to break down. But for a great number of cases, this is all you need. It starts to break down when you have to add magnetism. Okay? And we'll get into that later on.